Welcome back, everyone. In this lecture, we're going to discuss the concept of sampling error. Now, remember from our last video that when we take a sample from the population, we're taking a smaller subsection of the whole population to actually analyze. And that means that we're going to need to estimate the actual population characteristic by calculating statistics on the sample itself. The population characteristic that we're interested in is known as the population parameter. The word estimate is important here because it denotes that we are never 100% certain in our calculations for the population. This uncertainty is known as our margin of error. The margin of error's official definition is the greatest expected difference between the sample statistic and the population parameter. What we can do is we can use the margin of error to establish a range of values that we believe pretty confidently, still not 100% certainly, but pretty confidently, that the population parameter actually exists in. And I'm going to do an example to clarify what this actually means. So say, for example, we have this population. Again, we're going back to my fancy circle. And we want to know the average age of everybody in this population. Now, we don't have the money or the personnel to conduct a census survey. So what we're going to do is we're going to pull a sample of 100 people out of the larger population. So we pull them out. There we go. Now that we have our sample, we're going to ask everyone in our sample what their ages are, and then we're going to calculate the average age for our sample. So we calculate our sample statistics, and we find that in those 100 people, the average age is 25 years old. Now, we also discussed that our margin of error is plus or minus 2 years. In a statistics course, you're going to actually learn how to calculate the margin of error. But for the purposes of this class, I just want you to be able to interpret what a margin of error is and how to use it. But you will never be asked to calculate it yourself. So then, now that I have my sample statistics, the question becomes, how do we get the average age for the population from this average age that we've calculated for the sample? We do this by creating what we call a confidence interval. This is a range of values that contains what we hope is the true population parameter. The confidence interval is a super simple calculation. What you do is you take the average from the sample and you first add and then you subtract the margin of error from that number. That creates a minimum value from the subtraction, a maximum value from the addition for our population estimate. In this case, we take our sample average of 25 years old, and we both add and subtract the 2-year margin of error from the average. So 25 minus 2 is 23 years old, which is now our minimum estimate, and 25 plus 2 is 27 years old, and that's now our maximum estimate. This gives us a total range of 23 to 27, meaning we're not 100% sure that the sample average is the exact same as the population average. But we can be pretty confident. There's a magic number, 95%. Won't get into that. That's a statistics course. But we can be pretty confident that our population average age is somewhere between 23 and 27 years old. Okay, so what does this actually mean for your real lives, right? Well, you'd be surprised, but the concept of a margin of error is really relevant to everyday life because you see this type of research data provided a lot more often than you think. As we navigate towards a presidential election, you're going to see polling predictions everywhere. Everywhere you look, you're going to see numbers and data that are designed to explain who is going to win and how many votes. All of these predictions will include a margin of error because they're all estimates, right? Now, I should probably restate that, though, because not all of the predictions will include one, but predictions of valid polling research will include a margin of error. If you don't see a margin of error, it's not discussed, that may be a sign that you're not looking at a very scientific poll. Okay, so how do we analyze this information? It's really easy. When you're reading an article that's showing you polling data, you're going to take the statistics they calculated from the sample and add and subtract the margin of error that they have also provided to you. All right, so this poll, for example, was produced by our UT Tyler Center for Opinion Research. The poll showed that at the moment of polling, 46% of the sample would vote for Joe Biden and 41% of the sample would vote for President Trump. But remember, These are numbers that describe the sample, not the population. So using this data, the question is who would actually win if the entire United States had voted at the time of that poll, all right? So when you're reading an article that's showing you polling data, you want to take the statistics they've collected from the sample and add and subtract the margin of error that they provided to you. Again, remember that a good scientific poll will give you sampling information, and that should include a margin of error. If they don't discuss this, or maybe at least link you to the original study, that can be a red flag that the research may not be as scientific as you would expect. So watch out for that. So here are important numbers from that excerpt that I just showed you. Joe Biden is at 46%, President Trump is at 41%, and the margin of error that they gave in the article was 2.24%. So let's look first at Joe Biden's numbers. The percentage of the sample that voted him was 46%. So we're going to take 46 and we're going to add and subtract the margin of error, which is 2.24. That gives us a range of 43.76% to 48.24%. So based on the polling data collected, at the time of the vote, if held nationwide, Joe Biden would have received somewhere between 43 and 47% of the vote. We then do the same calculations for President Trump. The percentage of the sample that voted him was 41%. So we take that 41% and then we add and subtract the same margin of error. That gives us a range of 38.76% to 43.24%. So based on the polling data collected, President Trump would have received somewhere between 38 and 43% of the vote if held nationwide the day of the poll. Now we still need to answer the question of who will win, right? The margin of error introduces some uncertainty into the sample measurements. So to figure out who will win, the best way is to put the confidence intervals side by side. So let's plot this on a quick graph. If the lowest part of the graph is 35 and the highest part of the graph is 50%, then Joe Biden's range of possible votes is shown here with an arrow on the left, and President Trump's possible range of votes is shown with an arrow on the right. The two arrows do not overlap. That means even the lowest value for Joe Biden is still higher than the highest value for President Trump. This poll then concludes that Joe Biden would win the election. No matter what they are in that range, it's still going to be Biden outweighing Trump, right? So let's try another example. So these are from another UT Tyler poll, this one done several months before the poll that we just looked at. In this example, Trump is leading Biden 44 to 42%. The article gives you the margin of error as plus or minus 2.87%. I'll walk you through the calculations in a minute, but I'd like you to take a second and try to figure out the confidence intervals on your own. Go ahead and pause the video to give you time to do that. Okay, got it figured out? Here's what I got. Looking at Joe Biden's numbers first, the percentage of the sample that voted him was 42%. So I took 42% and subtracted the margin of error of 2.87%. That gave me a range of 39.13% to 44.87%. So based on the polling data collected at the time of the poll done, Joe Biden would receive somewhere between 39 and 45% of the vote if held nationwide. Then I did the same for President Trump, taking his 44% and adding and subtracting the same margin of error, which gives me a range of 41.13% to 46.87%. So again, based on polling data, President Trump would receive somewhere between 41 and 47% of the vote if held nationwide the day of the poll. Now, graphing this one out, I can see that both arrows clearly overlap with one another. This is where the margin of error becomes so important. If the true number of voters in the population was at the highest for both candidates, then Trump would win. But if the true number of voters was at the highest for Biden and the lowest for Trump, then Biden would win. But if the true numbers were at the highest for Trump and the lowest for Biden, Trump wins again. What this is telling us is that this poll cannot guess who is going to be the real winner of the contest. It is literally scientifically impossible, based on the numbers collected, to argue that someone is winning or not winning the poll, because both people could reasonably win based on our estimation process. So what does this tell you? It tells you to remember that you must be a critical consumer. Look out for political polls and pseudoscience arguments that are based on the sample numbers only, without consideration of that margin of error. Remember, there is error in every discussion where a sample is used to describe a population. So, if the authors are not providing you with that error, or if they're making statements that ignore that error, then you need to be very aware of this, and you need to be very critical of what you're reading. Another thing you need to be aware of as a critical consumer is sampling bias. Sampling bias occurs when the sample does not look like the population for whatever reason. This could be because the sample had to voluntarily participate, and people who chose to volunteer were somehow different than those who didn't. Think about it this way. If I called you on your cell phone on a Tuesday at noon, and I asked you, would you participate in a 1-hour-long phone survey? Would you do it? Do you have an hour to spend on a phone call at that time of the day on a Tuesday? Probably not, right? In fact, most people in school, people who are stay-at-home parents, people who are working adults, they're not going to be able to say yes and volunteer because that's a busy time of the day, noon on a Tuesday. I got stuff to do, right? Now, who would be likely to say yes? Older adults who don't have children in the house, people who are retired, people who are unemployed, or people who are disabled who have that time during the day. So voluntary participation may be driving sampling bias, but it may not be the only reason that your sample doesn't look like the population. Remember that a good sample is one that captures the diversity of the population. And if you're using a small or homogeneous sample, then you're not capturing that broad diversity, and you're probably going to make biased estimates. So we want to think carefully about who the sample is comprised of and who they're trying to represent. Here's an example of that unrepresentative sample. I'm interested in finding out the favorite literary genre of college students, and I go to a Star Trek convention to gather my sample. My sample says that their favorite literary genre is science fiction. Can I then conclude that all college students prefer science fiction books over others? Would you believe me? Hopefully you said no, you wouldn't, right? What is the problem with my research? It's pretty obvious, the representativeness of my sample. My population that I'm trying to generalize to is all college students, but I'm only gathering people from a Star Trek convention. Well, this means that my sample is heavily biased towards those individuals who would attend a Star Trek convention, meaning that they probably enjoy science fiction novels to begin with. This sample doesn't represent the diverse opinions of college students, and any conclusions I make from this sample about my population are going to be biased. All right, well, that concludes our discussion about sampling error. In the next lecture, we're going to move our discussion to the specific methods of sampling, starting with sampling methods that use random selection.